All right. So, in the previous lecture, I did explain about Lagrange's multiplier because we have to use this approach as we are having an optimization problem which is under constraint. Okay, so the margin which we want to optimize, its equation was given as 2 by w. We want this margin to be maximum, so it can only be maximum if w will be minimum because it is in the denominator. Since we need to perform the differentiations, partial differentiations, so we'll not take w, we'll take w square. And for further simplicity, we do take w square by 2. So we are making w square by 2 as our objective function. Okay. And we need to perform the optimization of it. For optimization, we do have a constraint equation which is given as yi w xi plus b minus 1 greater than equal to 0. This is the constraint equation. Okay, fine. So we do have w square by 2 as objective and this as constraint, and according to Lagrange, okay, Lagrange's multiplier, it says that f plus lambda g is equal to L. Either you can use f minus lambda g equal to L. You can use accordingly whether it is plus or whether it is minus. Okay, fine. So f is your objective, g is your constraint, and lambda is your Lagrange multiplier. Yesterday, I told that this multiplier lambda is having importance, and we can correlate this thing with the regularization technique which we have studied previously. Okay. And the regularization was to control. What to control? See, here f will behave under constraint g. So if I change g, it will put impact on f. So how much impact it will put on f, that I can control by lambda. That's what I can do. Okay. Therefore, it's a multiplier. Okay. And it is being called as a slope. Lambda is a slope of the constraint surface at the point of the tangent to the surfaces. We'll call this lambda as a slope. Okay, fine. So there are few things which I did mention related to the Lagrange multiplier, and we do have some rules also, like KKT rules, which relates the same only, because all these concepts are interrelated. So let me share my entire screen and talk about KKT rule also. KKT, what it means. Yesterday class also I did explain, but now I am available with some words related to it. Okay, so here it is. Okay, KKT. These are the rules or the conditions that are used to find the best or optimal solution. So we are doing that only in SVM to find the optimal solution of a problem. We are having limits or the boundaries constraint we are having. We do have objective function and a constraint equation. Okay, that is also we are having. So these rules are applicable under these conditions. Okay, you should have an objective function, you should have a constraint, you should have stationarity. This condition says that the optimal point, the direction in which the goal changes up or down, shouldn't have any push from the constraints. In simple terms, this means that at the best possible solution, the main objective and the constraints are balance each other. So who is balancing? Lambda. Lambda will behave as a balance factor. Lambda will balance the trade off between the objective and the constraint. It is saying that change in the direction up or down, there will be a point, there will be a point. You can take a curve like this, or whatever be the equation of objective function b. So there will be a point where you can see up or down. Okay, so this is my like up, and this point I can see as down, whatever. So at these points, it is saying we need to balance. We need to balance f and g, objective function and the constraint. And who will balance? Lambda. What is lambda? Lambda is a slope. Okay, lambda is a Lagrange multiplier. It will be working as a slope at that particular point. So that will be a tangent at that particular point. So it's mentioned in conditions of KKT. Fine. Best possible solution. The objective and constraint should balance each other. So at that particular point where you are getting the best solution, they should be balanced, and the point will be marked, and we can make a slope from that particular point. Slope over that particular point. Okay, there will be primal problem, there will be dual problem. Okay, we have studied yesterday. Primary problem is the initial optimization problem. Dual problem comes after primal problem. Okay, fine. When you are unable to solve primary problem, then dual problem come. Slackness should be there. So it's like a balance rule. It says that each constraint, the constraint is fully used its tight, meaning the solution lies right on the boundary defined by a constraint. Or if the constraint is not active, not impacting the solution, then the weight Lagrange multiplier associated with it should be 0. Okay, that means it's saying um, constraint should impact your objective function because you are solving the objective function under constraint only. And if it is not impacting, if it is not active, that means your Lagrange multiplier is 0. You are writing now that minus lambda g. So if this constraint is not impacting f, that means lambda is 0, then I am only having f. So that will be unconstrained equation. So either it should be tight, active, or whether it is not active. Okay, that is controlled by this Lagrange multiplier. So this statement is for Lagrange multiplier only. So whatever we have studied, it comes like this equation is followed here, Lagrange multiplier. Rest we did studied previously also, and I have revised. Okay. So the conditions for the KKTs are either you have to maximize or minimize the function, whatever. Okay, right now we want to minimize W. So let us suppose we are having a function to minimize this f of x, and we are having certain constraints. It should meet the constraints. These are certainly the constraints. Okay, which it should meet. Okay, and stationarity, primer, feasibility, dual, complementary. That all I have explained. You can read it. Okay. Meanwhile, we do have. Okay, I just want to remind you again, solving f under g, obviously there will be points, there will be points, because now remember one thing which is very, very much important. In margin, my initial lectures, I explained hard margin and soft margin. Okay, hard and soft margin. Hard margin is a margin which can clearly separate class A from class B. Okay, we are having minimum errors here, minimum, or misclassification minimum. Soft margin is a margin where we are affording the errors. If we can't separate the classes by hard margin, then obviously we need to apply the soft margin. Okay, that means we are affording errors up to certain level. Okay, affording errors. That is a soft margin. We are having misclassification. Okay, we know that. Since the goal is to increase the margin, we are increasing it. Because of the increasing in the margin, we are having errors. And okay, but the error should not be getting more. That means you have to follow the concept of soft margin. With some errors, you continue, but if the errors goes on increasing, reduce the size of margin. Reduce margin. Don't extend it more. But if your data is somehow not available, the data points are like far away from each other and classes are easy to separate it, then we are having a hard margin. Hard margin, that means we are having the max margin, maximum size of the margin. That's what we are having. They call it as, okay, we do have overfitting in this case. We may have overfitting in this case because here you are saying that the classes are linearly separable, and we have minimum error or no error. That means you are getting 100% accuracy here for classification. But in the real world problems, that's not the case. Okay, with soft margin, we are not saying that you are getting 100% accuracy because you are affording errors. There are errors, you are having misclassification, so you'll be having the accuracy like 90 to 95%. You may get such kind of accuracy. Okay, so in real world we can afford such case with soft margin. Okay, and whatever been explained here, like in KKT and in Lagrange multiplier, all are related to this concept only: hard margin and the soft margin. We are optimizing objective function, that is the W. Okay, in regards to this only, because W 2 by W is margin. We want to minimize it. That means we need to maximize the margin. But how much we can maximize? For that, we are looking forward to get an optimal solution under the constraint equation. So definitely we will get the points. Okay, and those points, the one which is the optimal point. What point will be optimal? I would say these are the support vectors. Okay, because margin now you have seen this is your, let us suppose, hyperplane. This is your class boundary A, this is your class boundary B. So whatever be the points which are present here, these are the support vectors. Okay, and this depth, or I would say the distance between the class boundaries, that is called as a margin. So I'm looking forward for support vectors now. These will be the optimal points. So optimal points will be the support vectors. Okay, so you should relate the terms. And where I'm getting the point, wherever I'm getting the point, what they told. Okay, you're getting the point, and they told there will be up or down. Okay, there will be up or down. See, here it's mentioned. The condition says that the optimal point, the direction in which the goal changes, up or down. What is your goal? The goal is to find the optimal point. And if at that particular point your direction changes, either it is up, either it is down. So obviously, if you are like this, so this is down, this is up, goal changes. If you are going like this, now you are going like this, from up to down you are going. So obviously you are getting peaks, or you may get the downfall at the optimal points according to the constraint and in your objective function. So it is saying that that means the best possible solution lies here, and it should balance, and the constraint balance each other out. What is the balance? Lambda will balance between f and g. Okay, so obviously there is a high level of maths in here. I do have one more algorithm, that is sequential minimal optimization, SMO algorithm. So this thing SMO came in your SVM maths. Here when I was following this sheet, this SMO came. Okay, so let me show you. Here it is: sequential minimum optimization. The dual problem offers advantages in computational interpretation, and in solving the dual problem, it is computationally efficient, especially using the technique SMO. So, what is SMO? Obviously, you will stuck in dual problem. I already told. And to solve the dual problem, it's saying that you have to follow SMO, sequential minimization optimization. Okay, so what this SMO is? Okay, let's discuss SMO. It is an algorithm used for solving the optimization problem. Obviously, now I will be having dual optimization problem. Okay, fine. So in context of SVM only, especially for training SVM is in a more efficient manner. SMO was introduced by Mr. John in 1998. So it's like a older algorithm, not new one. But in this year also, maths is something, maths, it never gets old. Everything is dependent upon maths. Okay. So especially for SPM to work in an efficient way, dual problem, SMO came. The goal of SUM is to find optimal hyperplane that maximizes the margin and separate the two classes. Okay, so how is this gonna done? This involves constraint optimization problem, which can be complex due to number of variables and the constraint. Okay, you are having many variables, you can have many constraints. Okay, so what you can do with the SMO? SMO simplifies breaking down the large optimization problem into small. This thing we have studied. Divide and conquer. I hope if you have an idea about algorithms, in algorithms we are having divide and conquer. That's what it is saying. They divide large problem into small problem, and these small problems in only involve two variable. Okay, now to solve two variable it is easy, to solve multiple variables it is tough. Okay, so let's solve two variables only. Okay, fine. So that is why it is called as sequential minimal optimization. Minimal means this only, small. In dual formulation, the optimization problem is quadratic in nature with constraints. The objective is to maximize the margin, which is equivalent to minimize a function related to support vector. Okay, so what is the function related to support vector W? I need to minimize it, then my margin will be maximized. So the Dewar formulation of SVM only depends on the inner product between the input vectors, which simplifies the problem. Okay, so inner product between the vectors. Okay, it's saying something related to it, that here optimization depends on the inner product between the input vector. We need to perform inner product. Okay, I would say it will be like dot product. And what is input vector? Kernel function. What is kernel function? What is a kernel? We have seen in the initial class there are so many kernels here. We are having linear. Right now we are talking about linear only. Linear, that's a hyperplane, that line linear. That is one of the kernel. We can have a sigmoid. We can have RBF, radial basis function, sigmoid function, poly. This is also a kernel function in SVM. There are many kernel functions in SVM. So it is saying that we need to find the dot product between input vectors to simplify the problem. And don't solve the complete problem. Divide the problem into two variable. And that can be done by using Lagrange multiplier. That's why we are using Lagrange. And let's solve these two variables. Optimization of these two variables is done, keeping other variable fixed. Okay, just two variables for solution. Rest fixed constant. Then any other two rest constants. Then any other two rest constants. This is how you can solve. Choosing the two variable. Which two variable we can choose? Okay, let's take alpha one and alpha two. At each iteration, select any two multiplier. Any multiplier you can select. Any two that corresponds to two support vector. That's what I'm saying ना. इनपुट जो है, इनपुट डेटा पॉइंट ही है. इनपुट क्या होगा? डेटा ही तो होगा. डेटा पॉइंट्स विल बी द इनपुट, एंड वी आर गोइंग टू कंसिडर देम एज अ सपोर्ट वेक्टर, एंड वी नीड टू फाइंड अ डॉट प्रोडक्ट बिटवीन देम, और एंड वी हैव टू सिलेक्ट टू rest constant. They are called as Lagrange multiplier. The algorithm computes the optimal values of these two variables. Okay, it will find the optimal value, and obviously this reduces the complexity. If we keep on trying to solve the entire problem, then that's not something good. Just take 2 2. The values of the two chosen Lagrange multiplier are updated based upon the optimization step. Then it meets KKT condition. Okay, you very well know about the KKT. If the conditions are satisfied, the optimization proceeds to the next step. You know what are the conditions for the KKT. Okay, and this is iterative in nature. Let's keep on selecting the pair of Lagrange multiplier. Okay, alpha 1, alpha 2. Okay, then it can be like alpha 3, alpha 4. Then it can be alpha 5, alpha 6. When alpha 1 and alpha 2 are there, then alpha 3, alpha 4, alpha 5, alpha 6 are constant. These two I will find the value. Then I can take any other pair. This pair I can take. Until you don't got the convergence. Just the algorithm will work. It will try to identify the support vectors. That what should be this class boundary? What should be this class boundary? I need to find the data points where this class boundary should be present. This is very high level maths. Okay, it will start from here. Okay, then it may start from here. Then it will look out for here. It will take the pair of data points and just try to find whether, okay, can you be a support vector? Can you be a support vector? So it's like a recruitment process. Okay, it's like a recruitment process. Who will be the support vector? So that I can have an optimal hyperplane maximum margin. Who can do this? For that only we are having so many points here. So it is saying that, okay, let's consider these as these data points. Okay, then call it as Lagrange multiplier. Okay, we are having f plus g lambda. Okay, so just put the values here and solve it. Follow some KKT rules. In SMO, just take two pair. So SMO for two, just considering two multiplier, alpha 1, alpha 2. For iteration number 1. For next iteration, take another pair. For next iteration, take another pair of data points. And rest will be like constant. Okay, that's what you have to do. Okay, fine. So, yes, so we can handle the constraints. We are having the bounds, and the SVM optimization prevent the solution from violating this constraint. Okay, this constraint will not be violated. We are already having a control with lambda, Lagrange multiplier with data points only. So many things are interconnected. Okay, and we are having some advantages: efficiency, simplicity, convergence. Are the advantages of SMO. Okay, and it's an efficient algorithm. Okay, it's one of the efficient algorithm which you can use to optimize the support vector machine. Okay, fine. So Again, we get back to our problem. So you are trying to solve this thing, or you can write it as w square by 2 under this optimization problem of like this is a constraint. So I'm having this as objective function, this is a constraint or need to perform the optimization. Okay, and let me write this in a format like Lagrange equal to L equal to wi square by 2. I can take minus, I guess here it's a minus is mentioned. Okay, minus. You can take plus or minus. Okay, let's go ahead with the minus. Minus lambda into yi wi xi plus b minus 1. Okay, this is my Lagrange. Okay, I1 to L. Okay, so I can have L multipliers, L Lagrange multipliers. That's what I can have. Okay, not Wi, it's W square. Okay, this is just W square. Okay, just take it as W. So, what I am having? Xi, Yi, and lambda I. Okay, this is lambda I. And it will be like summation I equal to 1 to L. So, I can have L Lagrange multipliers. They will be like as a support vectors. Who knows how many support vector will come? That is subject to the solution of this particular problem. Okay, so once I'm having this equation, okay, I can perform del L by del W, del L by del B, then del L by del lambda. This thing I can perform. Okay, and that's what they have done here. First, they multiply lambda I inside, so I'm getting this thing, and then they perform this del L by del W. So here the partial differentiation is with respect to W. I am getting W minus, here I am having W, so lambda I yi xi will be in the multiplication. This is equal to 0. Del L by del lambda I can do with this thing. So I'm getting here this lambda will be differentiated, rest all will be here available. Okay, so minus 1 and del L by del B. So this will be 0, this will be 0, only yi and lambda I in the multiplication. So I'm going to get this. And yesterday also I have solved. If you want me to do again, that's not an issue, it's very easy. You can differentiate this equation. Just differentiate this equation with respect to W, B, and lambda. You will get all these terms. And what they did is, because we know na, after performing the partial differentiation, we equate the terms to 0. That's what I have taught you in Lagrange's multiplier, equate it to 0. So if I equate this thing to 0 and this thing to 0 and this thing to 0, well, I'm not getting any answer for what is like what should be the value of x, what should be the value of y, what should be the value of lambda. You can do it. Okay, from first here I'm getting W equal to lambda I yi xi. Okay, so W is equal to summation of I equal to 1 to L lambda I yi xi. This is my first. That's the value of W. But in order to find W, I should be knowing lambda I. Okay, what's next? Next is I am having this lambda I yi equal to 0. Okay, so summation lambda I yi equal to 0. So I can use this ahead. I can use this thing ahead. Okay, fine. Then What's next? With this, I'm getting something. I can say summation yi w xi plus b equal to 1. That's what I can say. Summation I equal to 1 to L. Then it is like yi w xi plus b. Okay. And that's equal to 1. Okay, but still I'm not getting the value of what it means to be x, what it means to y, what it means to lambda. Okay, these two are the relevant equations which we got from above. So above is your primal problem. This is your primal problem. This is the result which you got from primal problem. Primary problem, your initial optimization problem, but you are unable to find what is the value of x, what is the value of y, and what is the value of lambda. You can see here, I can't claim anything. I'm not getting anything here. Only these two relevant equations I got. So what is dual problem? Dual, in the dual problem, now what we will do, we will again take our primary problem. Okay, we will again take our primary problem and we will substitute the value in primary problem, the value of w. Okay, that's what we will do. We substitute the value of w in our primary problem. In this problem only, here. Here we will substitute the value of w. That will convert it into dual problem. Okay, fine. So here it is. Again, write your primary problem, optimization problem, w square by 2 lambda I y w x I plus b. This is your primary problem. Substituting the value of w which I got from above in this same equation, जहां से वैल्यू आई थी w की, उसी में w की वैल्यू वापस रखने का, सेम, from where I got the value of w, put the same again inside it. क्या करें, और तो कुछ है नहीं ना मेरे पास. I got these two, and I need to solve my problem. I don't have any other direction to work upon. So what I will do is I will put up the value of w in the equation, and wherever I'm getting these, like combination of lambda y equal to 0, I will substitute again. I will substitute again this thing to make it 0. That I will do. Okay, got it. So this is how we have to proceed. Let's see. Here a value of w is been substituted. Lambda I yi ka square. Here also value of w is substituted. Okay, and just to change, just to show the change, you can see here the notations are changed. Now they are writing lambda j yj, lambda I yi. They did changed the notations. Here w in substitution still lambda I yi xi ka square. Here they have changed lambda j yj, lambda I yi xi xj. So this is the value of w. You can see w here substituted. Okay, got it. And this is lambda I. Then okay, they perform the multiplication. Okay, there will be multiplication. Above equation is a dual optimization problem. The equation are looking like scarier because of the substitution value of w. Because obviously it's scarier, no? Obviously it's scarier. And you can see, okay, this is lambda I yi xi ka square. That will be a matrix. This is a matrix. This will come to be as a matrix. Oh, okay, it's a matrix square. And we know, we have studied previously, matrix square can be written as matrix ka transpose dot matrix. Same thing they have done. This transpose multiply by itself. Okay, transpose by itself. Okay, then okay, here also the multiplication has been done.
Sir, screen not visible.
Screen is not visible. I haven't
Huh.
shared the screen, entire screen. You can see now this is screen.
So, but right now only.
Yeah, this is screen now. I was sharing this only. This is screen. Can you see this screen? Previously also.
Previously, thought it visible, but right now only the within the.
Okay,
Just
it is visible.
I refresh.
मैम I think it's got freezed at here. आपके end पे freeze हो गया होगा. यही
Maybe.
screen है.
Okay.
यही तो screen है मैडम. That's what I'm showing. अभी I am not teaching anything else.
Okay.
Okay, all right. ठीक है. तो ये चीज़ है. Fine. I hope now my screen is visible. ओके
Yeah,
ये
sir.
दिख रहा
No.
होगा. ओके ठीक है.
Sir,
मैडम क्या,
visible,
हाँ
visible.
विजिबल है ना. तो ये
Okay.
मल्टीप्लिकेशन भी करा. वी डिड द मल्टीप्लिकेशन. ऑलराइट. तो ये ऐसा करके कुछ टर्म्स आ गया. दीज आर द टर्म्स केम. अब देखो यहाँ पर लैम्बडा जे वाई जे आ गया. समीशन ऑफ लैम्बडा जे वाई जे. क्योंकि लैम्बडा जे वाई जे बोले या अदर वी कैन से लैम्बडा आई वाई आई, तो वो जीरो के बराबर था, तो ये थर्ड टर्म तो जीरो हो गई. ओके, दिस इज जीरो. हो गया खत्म. और फिर उसके बाद मुझे ऐसा फील हो रहा है, ये सारी टर्म्स लैम्बडा आई वाई जे वाई आई एक्स आई, ये तो उसने उठाया साथ में. ऑल दीज टर्म्स इट पिक्ड. ओके, इट पिक्ड. ये हुआ ऐसा कुछ होगा. दिस बाई टू माइनस दिस, ये सब एक जैसी टर्म्स है. लैम्बडा आई वाई आई एक्स आई, लैम्बडा आई वाई आई एक्स एक्स आई करके कुछ है ऐसा. तो कुछ इंटरनल सोल्यूशन है corresponding to that, half of this value minus this value, that will be this value. ऐसा करके कुछ उनका सोल्यूशन है. थर्ड टर्म तो जीरो है. एंड वी कैन री राइट दिस इक्वेशन आईडी इन दिस वे. ऐसा अपन लिख सकते हैं उसे रीराइट करके. कुछ अजम्पशंस करने पड़ेंगे. देर आर सम अजम्पशंस वी नीड टू फॉलो. ठीक, इतना तो अपना बना. और उसके बाद फिर ये बोला कि ओके, यहां पर वाई आई वाई जे एक्स आई एक्स जे, इसको डिनोट करा के आई जे से. ठीक है, जो कि आप खुद समझ रहे हैं. ये कह रहा है कि वाई आई वाई जे, ओके लेट्स टेक वाई स्क्वायर एक्स स्क्वायर, ऐसा कुछ अज्यूम कर लो. तो वो भी मैट्रिक्स हो गई. तो मैट्रिक्स हो गई तो वो उनके ट्रांसपोज का मल्टीप्लीकेशन हो गया. वाई ट्रांसपोज का वाई से, एक्स ट्रांसपोज का एक्स से. तो कुछ अज्यूम कर लो ऐसा इनको भी बोल दो, तो उसको फिर फाइनली के बोल दो. लेट्स कॉल इट एज के. और यहाँ पुट कर दो. और ये भाई हमारा लैम्बडा स्क्वायर, लैम्बडा भी है ना, लैम्बडा आई लैम्बडा जे, ये भी लैम्बडा स्क्वायर ले लो. तो लैम्बडा स्क्वायर हो जाएगा तो लैम्बडा ट्रांसपोज और लैम्बडा हो जाएगा, तो ये लिख दिया उसने. तो ओवरऑल इसने इतना सिंप्लीफाई करके बना दिया. लैम्बडा ट्रांसपोज लैम्बडा इंटू के बाय टू करके ये बोल दिया कि ये मैक्स ऐसा कुछ होना चाहिए। ठीक है, इतना वो बोल दिया। ठीक है, ये आपकी फाइनल इक्वेशन बन गई। और फिर क्या बोला, नेक्स्ट की जो आपका डब्लू था, गॉट दिस एज डब्लू। ओके, एंड अबाउ, अब क्या करना है, सो द फाइनल, सो दिस इज द फाइनल ऑप्टिमाइजेशन प्रॉब्लम, ये जो आया आपका, ये फाइनल ऑप्टिमाइजेशन प्रॉब्लम है। ओके, to find the maximum value of lambda, here more than k terms is there, and is nothing but the dot product of input variable, यानी इनपुट का डॉट प्रोडक्ट है वो, क्या आप देख ही तो रहे हो, वो बोला था ना इनपुट का, इनपुट क्या है, तो इनपुट x और y है, तो इनपुट x और y है, उनका डॉट प्रोडक्ट है ये, वेक्टर ले लो, मैट्रिक्स जो भी है अभी मान लो, तो उनका डॉट प्रोडक्ट है ये। यही हमने नोट्स में पढ़ा था, अब यहां देख भी लिया सामने की डॉट प्रोडक्ट जैसा आ रहा है इनका। ठीक है, तो बोला कि चलो ये डॉट प्रोडक्ट है, सो वी नाउ हाउ डू वी सॉल्व द अबव प्रॉब्लम, उसको सॉल्व कैसे करेंगे, तुम एक के बाद एक प्रॉब्लम अटकाते ही चले जा रहे हो, प्राइमरी प्रॉब्लम से ड्यूअल प्रॉब्लम, ड्यूअल प्रॉब्लम से इतना कर दिया, और उसके बावजूद भी अभी बोल रहे हो इसको भी सॉल्व करना है, तो वो कह रहा है एसएमओ लगाएंगे। एसएमओ मैंने बता दिया आपको कि भाई के जो है, के इसके कई, देर आर मेनी, बिकॉज समीशन ऑफ आई इक्वल टू 1 to L है वो। ठीक है, सो वी कैन हैव मेनी थिंग्स, ये बोल दिया ना, आई इक्वल टू 1 to आई कैन हैव मेनी, तो टू टू करके कॉम्बिनेशन बनाना है अपन को। विल यूज एसएमओ, देयर आर ऑल्सो वेरियस लाइब्रेरी सपोर्टिंग ऑनलाइन फॉर दिस ऑप्टिमाइजेशन, ऐसी का लाइब्रेरी जो सपोर्ट भी करती हैं, सो वी कैन फाइंड द वैल्यू ऑफ लैम्बडा, वो मिल जाएगा अपन को। और एक बार लैम्बडा की वैल्यू आ गई तो वाई आई एक्स आई तो डेटा पॉइंट है, उनको तो मैं रख दूंगा, तो डब्ल्यू आ जाएगा, और एक बार डब्ल्यू आ गया, वंस आई गेट द डब्ल्यू, तो यूजिंग डब्ल्यू एंड लैम्बडा, नाउ वी कैन कैलकुलेट बी, वो कह रहा है कि डब्ल्यू भी आ जाएगा, लैम्बडा भी आप निकाल दोगे तो बी भी कैलकुलेट कर लोगे फिर आप। ओके, तो ये कुछ ऐसी इक्वेशन है कंस्ट्रेंट वाली, दिस इज कंस्ट्रेंट इक्वेशन, हियर यू कैन पुट द वैल्यू ऑफ डब्ल्यू एंड देन यू कैन सॉल्व इट टू फाइंड द वैल्यू ऑफ बी, आप निकाल लोगे। ओके, ये बोल रहा है या पुटअप करो, और y की ये ऐसा कुछ वैल्यू यहाँ पर निकालेगा सॉल्व करते हुए। ओके, एंड दिस विल बी द वैल्यू ऑफ बी। ठीक है, इतना हम कर सकते हैं, बस ये आपका खत्म हुआ मैथ्स। ओके, फाइन, सो आई थिंक इतना डिस्कशन काफ़ी है आज के लिए, ये लास्ट लास्ट का थोड़ा सा और मैं एक बार रिवाइंड कर दूंगा, एंड देन आई विल स्विच अहेड। तो एसवीएम क्लासिफिकेशन में यही होता है, दैट्स व्हाट वी डू। ओके, गॉट इट। अब आपने देखा होगा कि कितना हमको अजम्पशंस एंड ऑल दीज थिंग्स फॉलो करना पड़ रहा है, कई थ्योरम्स आ गई हैं एसवीएम के अंदर, तब जाके हम कुछ समझ पाए, टर्म्स हैं ये, एक्स आई वाई, ये तो डेटा पॉइंट्स है, लैम्बडा है, डब्ल्यू है, बी है, ये निकालना है मुझे। सो फॉर दैट रीजन ना हम ये इतना कुछ करके चल रहे हैं। ऑलराइट, फाइन, गॉट इट, लेट मी स्टॉप शेयरिंग। ओके।